Okay, let's take a look at hypothesis testing. So this is the last chapter of statistics in year 12. It's also probably the most challenging chapter. So I recommend spending a little bit of time going through this really, really carefully. So this continues with the idea then of sort of dealing with probabilities in a more theoretical sense. It's very, very closely linked to chapter 6. Please make sure that you have mastered chapter 6 before you attempt this chapter. So hypothesis testing. Let's have a look at what hypothesis testing actually is. So here's our situation. I throw a coin 10 times. For what number of heads might you conclude that the coin is biased towards heads, and why? Let's have a think about that question. So, if you had 10 out of 10 times that landed heads, that would be quite suspicious, and that might sort of cause you to think that it was biased. But if you had, say, six out of 10, well, we recognize that the world isn't perfect. It won't always be 50-50, and that sometimes things happen by chance. So if we said 10 out of 10 is very sort of unlikely and suspicious, sort of intuitively to us, but 6 out of 10 isn't, well, you might ask yourself the question, where is that threshold in between that would cause us to think that some bias was going on or not? So have a look at the probability distribution. This is the sort of thing that we saw in chapter 6. This is how the test statistic, which is the number of heads, this is how it's distributed. So look, it's very, very unlikely, for example, that you get 0. It's as unlikely as that you get 10. The most likely result is 5. But it still only happens, I think it's about 20% of the time. So where do we start to say that, this result is a bit of an anomaly and perhaps this thing is biased? So the diagram suggests it's 9, or a value that's more extreme than 9, which would be like 10. So where exactly are those numbers coming from? Well, we'll see that a little bit later, okay? But we have the idea then that there are a certain number that are unlikely to happen by chance. It's possible, it's just unlikely, which suggests that perhaps the thing is biased. So a hypothesis is a statement, really, okay? And it's something that can be tested. So we can get some evidence. We can have a sample. That's kind of the link to earlier in the year. We get a sample, and then we can test the hypothesis. So what are we investigating? Well, we're investigating the idea of, is the coin biased towards heads? Sorry. So we have a probability connected to this, and this is what we really want to test. So, is the probability a half, which is sort of the underlying assumption really in the background, or is it more likely than that? Is it maybe more than a half? So to describe these two possibilities, we start with something called the null hypothesis. This is your default position. So if we were flipping a coin, your default position here is to assume that the probability is a half, isn't it? Okay, it's kind of so obvious it goes unstated. The null hypothesis is the default, and that suggests that it's a half. Well, what if that's not true? There must be some alternative hypothesis. So the alternative hypothesis here, you need to really read the context and the situation to pick this one out. Well, it's either not biased, so the probability is a half, or we said biased towards heads. So if that was the case, it means it's more likely than a half. Okay, so we need to start with these statements here, and this is often called H0 and H1. Okay, we'll get into the really mathsy sort of part later, but based on our number crunching, we're either going to say, yes, we're still going to say that it's a half. Okay, maybe it just got lucky, it's still a half. Or sometimes we might say, no, it's not a half, so it's this other thing here. This is kind of how we're going to use these a little bit later on. So, if we got like a number, like a small number, or a number up to a certain amount, we would say, well, we'll accept that the probability is a half. And, if you get a 7, for example, okay, it's less likely to happen, but it's not very, very unlikely to happen. Perhaps we just got lucky. We'd still accept that one there. But if we get a value of 9 or a value of 10, okay, we will say, no, 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 it's too extreme. It must be the alternative. The coin must be biased. So in a hypothesis test, the evidence from the sample is a test statistic. So, I'll link this back from before. We talked about capital X. Capital X is the thing that we're testing here, which is the number of heads, and this is its distribution. What else do we have? We're going to have something called a level of significance. Okay. This is something that's given to you in the question. Okay, this will always be given to you in the question. And this is what you're testing against. So for example, if I have a significance level of 5%, now this is the really tricky bit, okay? So bear with me a second. If we have a significance level of 5% and we do some testing, if this box here, the probability of 9 in 10 is less than 5%, so let's say maybe it's 3%. Let's pretend I've given you the number and I have told you that the chance that you get a 9 or a 10 when you flip this coin 10 times, sorry, that you get 9 or 10 heads when you flip the coin 10 times is only 3%. Well, if I said to you your significance level is 5%, what it means is anything less than 5% means that something is going on, something exceptional is happening. So I'm going to let you, I'm going to give you a tolerance of being lucky 5% of the time. But if it's anything less than that, we would say that the coin is biased. So if you have a number like 5%, and this one here is 3%, this would cause us to say, that the coin is biased, okay? We would reject our null hypothesis, and we would accept our alternative hypothesis, and the alternative hypothesis is that the coin is biased. Look what happens, though, if I change that number. If instead of 5%, I used 1%, okay, it means that my tolerance for just sort of getting lucky is quite different. This number has to be less than this number here for me to reject it. So because it no longer is, I would change my answer. So this thing, don't worry that you don't, look, it won't make a whole lot of sense yet. I understand that. But this thing, the level of significance, which is given to you in the question, this will affect your conclusions, okay? And whether you say things are biased or not biased. Okay. So hypothesis testing in a nutshell is we have some statement that we wish to see if it's true. This will be generally probability is something like this, or as you will see later, sometimes we'll have some statements like this. Okay, this is what number one will actually look like in practical terms. Number two, we collect some sample data by throwing the coin, giving us our test statistic. Okay, so we'll have some number to often to actually compare to. So before we had that graph of like the different distributions, the different outcomes, often somebody would do an experiment and they'll give us some data and we'll compare to that. We haven't really seen that yet though. Okay. Number three, if the number of heads or more is sufficiently unlikely to happen just by chance, then we would say the coin is biased. Right. This is a bit of a mouthful. So what does this mean? It means if the result that you see is really, really, really unlikely, let's say it only had a 3% probability of happening, by luck, by chance. Well, if this number is less, okay, if this is less than our significance level, that was 5% on the previous slide, what it will mean is it will mean that you reject the null hypothesis, you accept the alternative hypothesis. In other words, you would say that the thing is biased. Okay? If the significance level, if it's the other way around, so if the significance level is smaller, so in other words, if you have a big probability of the thing happening by chance, you would still just accept your null hypothesis. Okay, and that would be it. Again, don't worry, you're going to see this in practice. It needs to be drilled in like a couple of times to your mind. So, John wants to test to see whether a coin is unbiased or whether it's biased towards coming down heads. He tosses it 8 times and he counts the number of times that lands heads facing up. Okay, so what are our hypotheses? So the null and the alternative. What's the default position? The default position is that the coin is not biased, that it's a probability of 0.5. The alternative, you need to read the question for this always. You won't know unless you read the question. Or whether it's biased towards coming down as heads. So in other words, the probability is more than 0.5. Okay? Already we've started to, get into the realms of we would get credit for this in an exam, what was written. It's just part of the process, but it's a really important part of the process. You need to make sure this is correct before doing anything else. Okay. Those of you who are doing this as revision, this is a one-tailed test, by the way, because of the inequality sign. Okay, let's do some more complete examples now with some worded context. So, further example, an election candidate believes she has the support of 40% of the residents. That sounds to me like P equals 0.4, but we'll just check with the rest of the question. A researcher wants to test at the 5% significance level. So this is the thing that we will compare to, okay? This is the 0.05 that at the end of the question we will compare to. And we will say that if the probabilities are really, really exceptional and less than this, then we would say we'll reject the null hypothesis. But if they're bigger, then we will just accept the null hypothesis. We will keep with it. So this is something to come to at the end of the question. So we need to test whether the candidate is overestimating her support. So if she's overestimating her support, what does it mean? Is the probability 0.4? No, it's less than 0.4, isn't it? If you're overestimating, it's less than you think. The researcher asks 20 people. Okay, that sounds like n equals 20, whether they support or not, and 3 people say they do. Right. So what's the question all about? It's all about, do you support the person or not? So write down a test statistic. This is the number of people who support the candidate. Okay, and I would even put this one in here as well. So this is not, I mean, it wants X here, but just as a good habit, I write this in as well. So X is binomially distributed with 20 and 0.4 seems to be the idea. So write down 2 suitable hypotheses. Well, the default position is that the support level is 0.4, isn't it? That's what the candidate believes. And in this context, that's kind of the default. That's the thing that we need to prove wrong or prove right. So the alternative, the researcher thinks it's actually less. And the inequality line here is how we would sort of examine whether we look at the lower tail or the upper tail. And can you see here, because this is saying less than, we would look at the lower tail. That's what we would do. So explain the condition under which the null hypothesis would be rejected. Well, what we will do is we will test the probability of 3, because it says 3 people say they do. So 3 people, if you're talking about 40% of 20, what are you talking about? You're talking about, slightly less than 10 people? Well, 3 people is a lot less. So it sounds like it's quite extreme. So we need to look at the probability of 3 or fewer. Remember, we always group the probabilities together. If we go back here, we're not interested in just 3. We're interested in the lower end together. So I'm going to test the probability of 3 or fewer against the significance level. Okay, that's what I need to do. I need to compare this with the significance level. It's not asking us to calculate this, but we could calculate this. distribution mode on your calculator, binomial CD, and 3 or fewer. Well, 3 or fewer is this one, isn't it? This means 3 or less. And your calculator works that one out directly. You don't have to do anything else. Just if you're interested, this is 0.1, no, it's not, 0.01596, let's say. Okay, so we'll take this one here and we'll compare it to the significance level. When would it be rejected? Well, when this value is less than the significance level, okay, which is 0.05, this is when we reject H0. Okay, reject H0 and thus accept H1. That's what we would do. And if you're interested to know how the numbers link up, well, you get, what's this about? This is about 1.6%, which is a lot less than 5%. So that's actually what would happen in fact, okay? And if you put all of this together, this is what you'll be doing in part 7C. This is like a full hypothesis test if you do all of this together. Let's do another one then. So test your understanding, pause the video and have a go here. So I'm assuming that you've done that. So in the UK, 5% are late each day. So that's the null hypothesis effectively. What are we testing? Well, we're testing the number of students who are late. That's the test statistic, okay? That's what we're sort of counting, if you like. The hypotheses, well, the default is that it's 0.05. The alternative is that it's more. Why is it more? Well, if you had 40 students and you see that 6 of them are late, 6 is bigger than 4. You know, 4 out of 40 would be 10%. So what you see is more than like 10%, and you've been told that it's 5%. So you would be led to believe that, no, that number is too small. It's actually bigger than that number. The rate is higher than 5%. Okay? Well, when would we reject the hypothesis? So what we would do is we would look at the probability of 6 or more students being late. Now, why is it 6? Why is it 6 or more? In other words, why is it this one here? Well, you can follow the inequality. So when you say the probability is more, then you're looking at the upper end, okay? You can use this to decide later on when we do the probabilities, if you're looking at the lower tail or the upper tail. So because it says the probability is more, we're looking at the upper tail. So you would find the probability that 6 or 7 or 8 or 9, it lumps all of those together, okay? 6 or more extreme is what this means here. And then you would compare that to the 10% significance level. Now, we can actually work this out. You might remember from chapter 6, if you want 6 or more, what you do is you do 1 minus the probability of up to and including 5. Yeah? And if this probability is less than 10%, so if the probability of at least 6, if this is, less than 0.1, this is when you would reject the null hypothesis. In other words, you would say the chance of 6 or more people being late, just by coincidence, just by chance, is less than 10%. So because it's more exceptional than the significance level, it would lead me to think that something's going on and that our assumptions are wrong. The probability is not 0.05, it must be more. That's kind of the intuition behind it.